talk about Fourier transforms and sort of the different pieces and parts. And what I want to lead to this is to not just look at what is the baseline Fourier transform, which if you think about it is a way of talking about looking at a time representation, going to frequency, and then taking the inverse operation, which goes to time, which is defined by these two various integrals. Really is an orthogonality principle, right? I'm trying to figure out, hey, I know that sinusoids are orthogonal. I know that exponentials are eigenvalues of linear functions. These are all good stuff. And I can sort of take these sort of Fourier terms, multiply it against that over all things, and I get basically projecting on an orthogonal basis. Similar sort of thing allows me to go from frequency to time. And this turns out to be extremely valuable, and many different forms of this get used in many, many different places. But what's interesting, then you sort of say, okay, we use Fourier transform, and in a continuous time world, everything is cool. This makes a lot of sense. But there's a lot of times when we need these in discrete time as well. And so those have interesting parts. So when I look at discrete time, and sometimes people talk about discrete time Fourier transform. Sometimes you talk about this as a frequency response. Sometimes you talk about various pieces, but what you realize is that you typically have something sampled in time. And the fact that it's sampled in time also means that you are periodic in your frequency, which in this case is omega hat. But in this case, you're still continuous in omega hat. And so the discrete time shows up in a sum as an infinite sum. And so that gives you something to work with here. Versus then when you actually want to go back to the samples, you have an integral back over all of the frequencies for a particular n. So, okay, this gives you at least one form, and for dealing with sampled systems and looking for its frequency response, this works great. The thing is that often when I'm in a sampled system, I also would really like to be able to compute a Fourier transform. Well, if I'm in a sampled system, I'm going to be computing over a sampled set of inputs and a sampled frequency. So I need a different structure that sort of handles this in a way to kind of go from here to here and down. And so this is now going to be, I'm going to be dealing with n samples in time and n samples in frequency to kind of be able to build this structure. And there's a couple different ways we could have done that, but that's the way it typically gets looked at. And if you look at it in the forward domain, it now becomes a summation like we had before. But if you think about it, I'm only using n points, not infinite points to create this. It also means I'm dealing with a fundamental frequency. And for those who are used to thinking about Fourier series, it's kind of the reverse of this, right? It's reverse of the discrete time Fourier transform, where I'm saying, hey, I've got samples in frequency, but I'm continuous in time, right? And I'm continuous in time knowing I'm around a fundamental frequency. Same sort of thing should start, sort of those echoes should be coming back to you at this stage. And what you find here is that, yes, in fact, I can get a fundamental frequency. It's related to 2 pi over n, because here we're going to deal with frequencies instead of often plus or minus pi. We're going to deal with 0 to 2 pi. And this is relevant because, remember, it's going to have a 2 pi periodicity, so I can pick any one I want. Well, this is usually the one that gets picked. So that's what we're going to use. And so what you can show is that you're going to have this with a certain fundamental structure. Now, those who are curious, you can also go, hey, I can still use certain rules and break this out into sine and cosine. And of course, the minus sign here comes from the minus of that particular term, remember? So the transforms to the frequency domain always have a minus in the exponential. Those going out of the frequency domain are positive in the exponential. That gives me a minus here. And so this gives me a cosine and sine. In fact, these two pieces are so useful that they have sort of sub-functions. One's called a discrete cosine transform, one's called a discrete sine transform. And there's a couple different forms and flavors and varieties, but basically what is the imaginary and what's the real part? Yay. So again, ways to try to deal with the computation, because you start getting now into much more interesting computational questions. And the inverse, of course, looks a lot like the forward side of this, and that actually is very useful in terms of its symmetry. A couple of things are important, that all the way through all of these kinds of Fourier transforms, all the transform pairs are reversible. So if I have something that goes from time to frequency, that same functionality goes from frequency to time, just sort of swapping the variables. So if I can get one transform pair, I actually get two. So it's like kind of get one for free. There are some things that'll happen where people will do these as symmetric transforms, because notice the inverses have a 1 over n or a 1 over 2 pi in it. I can often sort of split the difference, and that'll be useful, particularly if I'm trying to talk about sort of having the same energy and not having to renormalize. That you'll see used a bit. But probably the biggest thing to notice is that in all of these cases you get convolution. Convolution becomes a product in its frequency domain. The funny thing with this one, in the discrete Fourier transform, is there's this thing called circular convolution. So it's not quite what you think it is, because everything is periodic and assumed to be periodic, and that tends to create actually more constraints. But otherwise, you get this in all these cases. And it's kind of useful, I think, to see all the frequency response questions all in the same place. So that way you can kind of see all of the relations and connections, and you realize what's happening when you're going from one orthogonal base, going from one basis in time, and then talking about things on a frequency basis, and then shifting it out of that basis back into time.